Then we can start the webinar. Today, April the 21st, we have invited for our On Things to Come webinar series, Professor Stefano Vitale from the University of Trento, my compatriot. Many thanks for accepting our invitation, who will talk about the LISA mission of the European Space Agency. I am Laura, I'm the PR manager of ISSI-BJ, and in the webcam, apart from Professor Vitale, you can see our executive director, Professor Weimin from Taiwan. And thank you very much, everyone, for being connected today and for listening in to this very interesting presentation that will be given by Professor Vitale. A couple of words about ISSI-BJ and our On Things to Come webinar series very quickly. If you've participated in our previous webinars, you probably already know what ISSI-BJ does and what this webinar series is about. But a recap, ISSI-BJ was founded in 2013. It's an institute for advanced space science studies, and it was founded thanks to the cooperation between the International Space Science Institute in Bern, Switzerland, and the National Space Science Center of the Chinese Academy of Sciences here in Beijing. ISSI-BJ, as I said, it's an institute for space, advanced space science studies, and therefore we organize several kinds of events to attract scientists to our premises to work together and on the research projects. We have workshops, we have forums, we have working groups, we have international teams, and our keywords are being international and multidisciplinary. Therefore, we try to arrange teams of scientists coming from different countries, from different continents to work together here in Beijing. As you might have noticed, we haven't organized any offline events so far in the past 2 years because of the current epidemic that we all hope will be over very soon. But in the meanwhile, we have this On Things to Come webinar series in English to address ongoing and future space missions. And once again, if you're slightly late, today we have Professor Vitale that will be introduced by Professor Ip. Many thanks once again for being here, and enjoy the webinar.
Yes, thank you, Lola. So today we have, it's really indeed our great pleasure, to have been able to invite Professor Stefano Vitale to present this exciting mission on LISA Pathfinder. And as he will tell you later on, how interesting this project might be to look for gravitational waves, etc. But first, a few words about Professor Vitale himself. He was graduated from University of Rome, summa cum laude, fantastic. And then he went to since then he went to University of Trento, yeah, and then spent all the time there. And but then he had made such a fantastic career. If you read through his appointment and the positions, you can find that for now he's the PI, principal investigator of the LISA Pathfinder mission, which is a major mission of ESA. And then you'll find that he is also vice chancellor of the University of Trento. And then he is a member of the ESA SSAC. And, I would say one of the most important committee in ESA. And then he is also a vice man on the board of directors of the Italian Space Agency. Someday I must ask him what he would do there as a vice man. A very interesting thing to do.
It was in the past. Yeah.
Maybe you could tell us later on. But then last year he was winner of this very important prize, the Tycho Brahe Medal of the European Astronomical Society. Congratulations! Yeah, congratulations! And so I would say that Professor Vitale is representing the kind of the great scientific achievement in astronomy of Europe over the last, I would say, 400 years. So with a lot of expectation, Okay, Professor Vitale, please go ahead. Thank you.
Thank you very much. And let me start thanking the Institute for this kind of invitation and the opportunity to share with you the enthusiasm for this mission. So this is a talk on LISA and LISA Pathfinder. LISA, as you may know, is a a project to fly a space-borne gravitational wave detector aiming at frequency between a few tenths of microhertz to a fraction of a hertz. It's a project developed by ESA, the European Space Agency, with all its member states, with robust support from NASA. So you may have heard of the big success of the ground-based detector, and you wonder why, if those ground-based gravitational wave detector work so well, you need a detector in space. The reason is that there is no hope to access those very low frequency from ground, mostly because of the gravitational noise due to the motion of the Earth's surface and the atmosphere. When I got this invitation, it was suggested that a little reminder of what gravitational waves are would be handy. So I have my $5 reminder. To understand what gravitational waves are, you have to embrace Einstein point of view, that the effect of gravity is mostly that of curving space-time. So if you have two particles that are flying together, when they are far away from the source of gravity, they go straight at a constant velocity and constant relative velocity. And when they approach a mass that generates gravity, the picture changes, the trajectory becomes curved, and even more important, the two particles see each other accelerating. So if you sit on one of the particles and look at the other one, when the mass comes nearby, you see the velocity of the other one changing in time. And actually, this is in reality the only effect of gravity you detect if you don't see the source, right? I did the source black, so you don't see it, but it could be just far away. And so the only effect of gravity you see is that particles accelerate one relative to the other. And by the way, in this little pathetic animation I did, you also see how one plans to measure acceleration of particle. You shine light on the other particle and look at the color of the light reflected. And because of the Doppler effect, if there is acceleration, there is a change in color. So that's what gravitational waves are. If now somebody changes the distribution of matter somewhere in the universe, that changes the curvature of space-time, and nothing can propagate faster than light. So this change in curvature, due to, here you see an animation from the Hubble Space Institute of interacting galaxies, right? We are talking enormous bodies that are changing the gravitational field somewhere in the universe, and the effect of these changes can only propagate at the speed of light. So if you work out the mathematics correctly, that you get that, as usual in physics, things that have to propagate at finite speed propagate like waves. And so that's what gravitational waves are. Waves of curvature that propagate at the speed of light, and that you can detect because they induce relative acceleration in among free-falling test masses. Okay, now you know gravitational wave as much as I know. Okay, so the idea of a detector like LISA is to use two spacecraft as those two particles, right? So if there is a gravitational wave, you measure an acceleration between those two spacecraft. They are far apart because you will see in a moment the effect scales with the distance. So you're talking million kilometers apart, and in reality, you need more than two spacecraft. The plan is to fly three, and so to fly three spacecraft, and so to do three of this relative acceleration detector going around the sun. But I'll give you more detail soon. So how the basic instrument works then? Well, the basic idea is that you have an emitting satellite that emits a laser beam toward the receiving satellite. If there is a gravitational wave, I don't know if you can see the cartoon, but the frequency of the laser that I described with the color of the beam changes while it propagates from one satellite to the other one. And the frequency shift between the source and the receiver is just proportional to this space-time distortion. It's what the experts call the metric tensor perturbation. Even more striking is that this change in color, this frequency shift that that the beam undergoes changes in time and oscillate at the frequency of the gravitational wave. And so the curvature, what the expert called the curvature, is proportional to the change in time of the frequency of the received beam. And notice in this formula that the effect scales with the distance between the emitter and the receiver, so that you want very large detector to increase the effect. And that's the reason of the 1,000,000 kilometer you have seen in my previous slide. So the idea is simple. You send a light beam from one satellite to the other one and look at the change in time of the frequency of the beam. Unfortunately, as you know, there are much more trivial way of changing the frequency of the beam. If you shake the source or you shake the detector, that's irrelevant. The standard Doppler effect changes the frequency of the received beam, right? And so there is in reality no way of distinguishing the two effects. And so if you measure the frequency here and you measure the frequency time derivative, yes, it may be contributed by gravitational wave, but it's also contributed by any difference in acceleration between the emitting spacecraft and the receiving spacecraft. And there is no way of distinguishing that. And when people started to discuss the possibility of having a space-based detector, we all soon realized that if you put two spacecraft in space nearby the Earth, they are subject to the solar radiation pressure. The intensity of the light emitted by the sun is not constant. And so this shaking sun intensity will shake your spacecraft and give acceleration that would obscure any interesting astrophysical signal. And so you have a problem. So if you try to do this experiment, this detector with just simply free-falling spacecraft, you are bound to fail because of the solar radiation pressure. But fortunately, physicists are ingenious, and so immediately the idea came, okay, let's carry with us a reference test mass. If you take a test mass which is floating inside the spacecraft, like an astronaut inside the International Space Station, because it's surrounded by the spacecraft, the solar radiation pressure will not hit the test mass. So the test mass is flying freely. And so obviously you should not be touching the test mass. So the spacecraft should be very careful avoiding the collision with the test mass. So this is done by measuring where the test mass is and feeding this information to a set of micro thrusters, a micro rocket that keep adjusting the position of the spacecraft such that there is no collision between the spacecraft and the test mass. And now you can measure the acceleration of the spacecraft relative to the test masses and correct your frequency shift signal for the acceleration of the spacecraft. And so the basic idea of this measurement is that you do three measurements. You measure the acceleration of the two faraway spacecraft relative to the local test mass that act as your inertia reference frame. So it's a sort of inertial sensor. Then you measure the frequency shift in the propagation of the beam from one spacecraft to the other one. This one is affected by the acceleration of the spacecraft, and so if you do your algebra with the proper sign, then the acceleration of the spacecraft, you add up and subtract the signal, the spacecraft acceleration enters twice with opposite sign and cancel out. And so in a sense, you now have reduced, like you were sending your beam directly from one test mass to the other one. Those are not affected by the solar radiation pressure, and so your measurement is clean. It's not completely clean, right? Because if the test mass accelerates relative to the local inertial frame, that will superimpose to your gravitational signal and anyhow will be a source of noise. And in a sense, a good part of this talk is about the source of noise, but this acceleration are expected to be much, much less than those of the spacecraft. And so the detector is now becoming interesting. Okay. If you're familiar with the ground-based detector gravitational wave, my colleague in LIGO or in Virgo send the light back and forth between their test masses that are the mirrors hanging from the ceiling many times, 100 times before they do the measurement. You cannot do that in space. Over 2 million kilometer distance, you don't get much light reflected back, a few photons if you start with a watt. So in reality, this is much more like inter-satellite communication, where each satellite sends a beam to the other satellite. So there are 6 beams traveling along these 3 arms of LISA, and the science signal are combination of these 6 isolated measurement of frequency you do on board of each spacecraft using the beam coming from the other 2 spacecraft. Before I go a little bit more into details on how the mission is done, let me tell you about the orbit. As I told you, we have 3 spacecraft in LISA, and this spacecraft form a triangle, and this triangle is pretty constant. What is surprising is that you don't need any engine to maintain this formation. It found that for one, it turns that for one of these miracles of celestial mechanics, if you put the 3 spacecraft in 3 heliocentric orbit, very similar to that of the Earth, properly tilted and phase shifted, the 3 spacecraft form a triangle that goes forever. It doesn't go forever because of the small perturbation of the gravity, but it basically goes for years and years. With the length of the distance within the spacecraft is not exactly constant. It changes by 100,000 kilometers, but over 1 million kilometers. And so, and the fact that this antenna, this gravitational wave antenna, goes around the sun is very important, because in a sense, because most of the gravitational wave are long-lasting, your sort of opening by turning the detector in the wave, you're doing a sort of a synthetic aperture telescope, which is very important to identify the position of the source in the sky. So if you want to give a closer look on how the instrument is done, now the basic instrument in LISA is what is realizing this frequency measurement of the received beam and the acceleration measurement between spacecraft and test mass. And so it's easy to say, but if you have to implement technically, here is the test mass, which is surrounded by a lot of accessories to make it usable. And then you have an optical bench where you do all the interferometry which is needed to do acceleration measurement and frequency measurement. In particular, you have a local interferometer to measure the acceleration of the spacecraft relative to the test mass, and you have an interferometer to measure the frequency of the received beam and to send the beam to the other spacecraft. This is done through a telescope, but mind you, this telescope is not used to look at stars. It's a telescope used to receive the light from a distant spacecraft and to send the light to the faraway spacecraft. If you want to give a closer look to the test mass, I can show you the test mass because I'll tell you in a second, we have flown one on LISA Pathfinder. The test mass is a cube of gold platinum, a couple of inches of size, a couple of kilos. Is surrounded by electrodes, so in flight is inside this box, but it doesn't touch in any way the box. There are millimeters all around this cube, and is floating inside this box like as I said, an astronaut in the space station. You see that there are electrodes here. The reason why we have to carry electrodes is that we can follow the test mass with the spacecraft in the direction in which we do the gravitational wave measurement, but in the other direction, unfortunately, we cannot. And so in the other direction, like in this direction, we apply little force to the test mass to keep it stationary in the spacecraft. And we do this with a very weak electrical field that are applied through those electrodes. And if you want a rendering on how all this would look like, this is now old, but the concept is very robust and so has not changed. And so you see here a 3D rendering. You open the telescope, you see the light beam coming from the distant spacecraft, the light being distributed on the optical bench to do all the frequency measurement, and then some light from the back of the optical bench goes into a series of Russian dollies. And in the center of the Russian dolly, there is this magic gold platinum test mass at the core of the instrument. The concept, as I said, has not changed very much. This is one of the last picture on how is shaping up now in the development of LISA in ESA. I'll get back to that. So I told you the effort is to enter this frequency range. If you want to have an impression, 10 in 10 to the minus 5 hertz means the inverse of half a day, right? So you're going from waves that changes over half a day to waves that change over a minute. And why, if you're so successful on ground, you want to go, you make this big effort to go to space to go into this frequency range. Now, the explanation is simple. The people show you that, for instance, if you have two neutron stars or two black holes orbiting each other, the gravitational wave frequency, the frequency of the emitted wave, as this cartoon should show, is twice the frequency of revolution. Basically, it's one wave crest per half a revolution of the two stars. And the frequency of revolution, with pretty good accuracy, is given from Kepler formula. Maybe you recognize the formula of the frequency from the textbook, right? Which scales with the mass. The larger the mass, the lower the frequency, and is inversely proportional to the separation between these two bodies. This R is the separation between the two bodies. Now, the separation between two bodies cannot get below what is called the Schwarzschild radius of the two bodies, right? When two bodies enter at the distance which is closer than this number, which was a discovery of Einstein, a kilometer for the sun, right? Then they merge into a single body and they don't emit any gravitational wave anymore. So R can be very large, but cannot be smaller than this number. So it's better to normalize this formula to this minimal separation, because that's the minimum distance at which the sources still emit gravitational wave. And if you do that, then you discover that the frequency of the wave is a decreasing function, diminishes with increasing mass and increasing separation. And so now you get immediately what you get by going through this terrestrial gravity noise wall and achieving low frequency. On one side, you get access to waves emitted by very massive object. Very massive means million times the mass of the sun in all their incarnation. And if you want an example, I think many of you are familiar with this animation. This is an animation made of pictures of stars around the center of the galaxies. This is a Nobel Prize animation because it's the Nobel Prize 2020 for physics. And you see stars orbiting. These are stars, right, that in less than the period of Jupiter are orbiting something which is invisible here. And we now know that this is a million solar mass, many million solar mass black hole, and apparently all galaxies have one of this huge monster in the center. And so when Hubble shows that galaxies interact gravitationally, in reality what you're seeing is the interaction between the black holes in the center of the galaxies that form a binary that start to orbiting each other, emitting waves at such a high rate, such a high power, because the power emitted is proportional to the product of the mass, and these are monster of million solar masses. And so the signal are visible with a detector like LISA. We predict that we should be able to see the signals from this monster wherever they happen in the universe, even at the beginning of the universe, even at the billion years from at any redshift. If for those of you that are astronomers and know what the redshift is, this event are visible with signal to noise ratio in excess of 100, even at the limit of the universe. And this is a simulation of what the LISA signal for one of these monsters looks like. There is no signal processing, right? The signal is low passed because you have to downlink the data to ground. And so just the low passing of the signal, and that's the huge signal to noise ratio for a relatively small one of just 100,000 and the astronomer have, and the astrophysicists and the cosmologists have very high expectation. For instance, because this system spins faster and faster and faster, sooner or later the frequency of the wave enters in the LISA band. And so LISA will see, will see at all frequency systems that are far away and far away and far away. And so in a sense, LISA will do a sort of cosmological stratigraphy of the event of a galaxies merger that form a bigger and bigger and bigger galaxies. And so retrace the history of formation of the galaxies nearby us from the merging of faraway galaxies from the beginning of the universe. And that's just a little taste of what you can do with these signals. Another one, which is very, very LISA, that you could never detect from ground, is if a small compact object, like a small black hole, falls in one of these monsters. So you see up there an animation in almost one-to-one time scale. And the orbit is very chaotic. It's not Keplerian because the gravitational field is very, very strong here. And the simulation is that, oops, I hope you're not hearing the noise, are you? Well, anyway, this animation is an accelerated animation of the orbit, and what you have seen is a very, very rich gravitational wave signal that all of a sudden disappears when the little body falls into the event horizon of the black hole, the black surface of the black hole. Then everything disappears. And so, for instance, the people say this will be a demonstration with very high accuracy of the so-called no-hair theorem of black holes, that nothing can come up of the black holes. I don't know if you have noticed that recently one of the European Space Agency mission, XM Newton, a veteran in X-ray, has detected, I don't know if you can see this animation, has detected peak of X-ray animation, and many think that this is the small body that periodically is punching the accretion disk of the central black hole. And so this is, in a sense, preparing one of these events that we call extreme mass ratio in spiral. The total opposite range of phenomena you achieve going low frequency is sources that are so well separated that basically they will never merge, not in our lifetime, right? And not in the LISA lifetime. And example of those are all sorts of binaries or compact objects in our galaxies. I will tell you a little bit more, including the binary black holes that LIGO and Virgo have detected so successfully. People have calculated immediately that if LISA had been up in the sky and measuring, would have detected this signal 10 years before LIGO, would have warned LIGO to prepare to see the signal, and the analysis of the signal at low frequency when the two bodies are still separated, and at high frequency has an enormous implication for the physics of the black holes. More mundane but impressive is this census of binary in our galaxies. These are mostly white dwarf binary. Some are so intense that we know everything about the signal because we observe those with electro in the light, they emit light. And so these were, in the old days, were called the verification sources for LISA to calibrate the instrument. But the people predict that LISA should be able to detect tens of thousands of those signals. Because the duration of the measurement is years and years, you have a microhertz discrimination, so you should be able to distinguish tens of thousands doing a big census. And on top of that, there will be so many that there is a sort of stochastic foreground of the one you cannot discriminate. Now, I'm not an astronomer, I'm a plumber, I'm an instrumentalist, but I just stole a few view graphs from one of my young colleague presentation on what the astronomer thinks to do by making this impressive census of our galaxies to complement the one you do in the visible with mission like Gaia. And what always amazes me is that the people think that we will be able to detect even planets of this system. So if there is a planet orbiting one of these binaries, the perturbation in the orbit of the binary will be visible in the gravitational wave signal. Needless to say, LISA has an embarrassment of richness. The signal, the data stream will be so rich that disentangling all this signal will be one of the big challenges, but I have no time to go into the details. If you're interested, just ask questions. So let me go back to my job, which is I'm an experimentalist. So what is the noise in LISA? What can LISA measure and what is the noise? So this is a plot of metric tensor noise. Never mind, it's in some unit the noise of LISA. So it's noise. So the lower you are, the better you are. It's as a function of frequency, it's a spectral density. And so at frequency between microhertz and millihertz, we expect to be dominated exactly by the fact that our perfect test masses are not perfect. And there will be disturbances accelerating those test masses and producing a frequency shift in the detector that cannot be distinguished by gravitational wave. At a higher frequency, obviously, you have to measure those frequency shifts. This is a noisy procedure. And so you will be limited by your ability to measure those frequency shifts with an interferometer. However, I told you, LISA is a low frequency detector. And so it's not surprising that most of the signal to noise ratio for the most interesting astrophysical sources of LISA is accumulated in the frequency range where is the acceleration of test masses that is limiting the sensitivity of the detector, right? And so you have to work on to keep this acceleration, to keep all the sources of forces that try to accelerate your test masses as small as possible. How small? This is a plot of the LISA requirement in terms of acceleration of the test masses. It's a spectral density, don't you worry. Look at the frequency, right? Days to minutes. And look at this scale. This is meter per second square. So the acceleration of gravity on the Earth is 10 in this scale. And in order for LISA to give full science return, the noise of LISA must be below this black line. This is noise. The lower you are, the better off you are. And so you see, this is 10 to the minus 14 versus 10. That's why we call sub-femto G acceleration noise, or force noise per unit mass. So we are in 1G on the Earth, so no way you can demonstrate that this is achievable with an experiment on the ground. It turned out that even if you try to do an experiment in the low Earth orbit, the lower Earth orbit is gravitationally too noisy. And so all the beautiful mission, gravitational mission of any sort, like geodesy mission that I've flown in low Earth orbit, even recently, cannot even think to reach this this very low acceleration. That's why when ESA was convinced that gravitational wave astronomy was one of the astronomy of the future, they said, let's put some money and demonstrate that this is feasible. And so they got the idea of having this mission, LISA Pathfinder. Thanks God, if you want to demonstrate that you can put test masses in free flight inside the spacecraft without too much of disturbances, too much of forces on that, this is a local problem, right? So you don't need the 1,000,000-kilometer separation between the two test masses. And so the basic idea of LISA Pathfinder was, okay, let's put two test masses inside a single spacecraft and measure the relative acceleration between them. So you can think like you have taken a LISA arm of a few 1,000,000 kilometers and squeezed into a single spacecraft to be a few tenths of centimeter. And so that's what LISA Pathfinder was two test masses in a single spacecraft, right? Two interferometer, one to measure the relative acceleration of the test masses, and the other one to measure the acceleration of the spacecraft relative to the test mass to implement the technique of the drag-free where the spacecraft follows the test masses. Unfortunately, if you have two test masses, you can follow only one at once, right? And so the spacecraft follow one test masses, and the other one, contrary to LISA, we have to apply a little force. We try to be as gentle as we can to keep these test masses inside the spacecraft and together with the other one, but we pay a price, and I'll tell you about the price. So that's the thing we flew, because we're talking in the past. 2 test masses, as I told you before, gold platinum, very dense, 2 kilos, a few centimeters, a single optical bench that I'll show you in a second, very stable. Everything is glass with all interferometer in it. The test masses are surrounded by those electrodes, a box containing those electrodes, we call the electrode housing. We have to do other tricks. You see, for instance, because the test mass is free floating, there is no grounding wire, right? And the test mass keep charging up because of the cosmic ray. So we have to discharge those test masses, and we do by generating a photoelectron with ultraviolet light. And we steer the photoelectron to neutralize the test mass. And this very delicate thing is still 2 kilos. So at launch, you had to block it, and it turns that you had to block with almost a ton of force, and then release with very high precision. So we carry a caging mechanism to hold the test mass at launch, and everything is in a vacuum enclosure, and I'll tell you more. So this instrument here, which is, 50 centimeter, half a meter size, goes into the center of a dedicated satellite. The center is the best place to put it. And then if you want to see the real hardware that flew, it's somewhere around the sun now. This is the test mass. You have seen already that. Now, the test mass and its electrode housing is integrated with all its accessories. But remember, the test mass is the end mirror of an interferometer. So all this thing must be aligned with micron precision and sub-millirad precision. And this goes to the credit forever to European aerospace industry. They did a fantastic job with those alignment. And an equal fantastic job was done by the University of Glasgow and the industry in doing the optical bench. This is a old glass optical bench, which is assembled with this technique of the silica bonding. You put a little bit of silica of sodium hydroxide in between, and in between the two pieces that you have to glue, and basically the glass is reformed. So there is no mechanical difference between having carved everything from the bulk. You got a minute to align the things, or a minute or a few minutes, and once it's done, it's done. And if you have done the thing wrong, you throw out everything. But nothing was done wrong, and the micron and sub-millirad alignment were gloriously achieved also on the optical bench. And then the system becomes very complex with all cables. And I mean, as a naive experimentalist, if you had shown me this 30 years ago, I would say it could never work. It's too complicated. But it did work, and worked very well. I'll show you. And again, it goes to the credit of all the people in industries and laboratories that work into it. You see the thing being assembled and put in this central cylinder, and then the central cylinder goes into the spacecraft, and the spacecraft with its propulsion module goes into the fairing of the Vega launcher, which is an Arianespace launcher fabricated in my country. And we launched it in December 2015. We had to navigate to a place far away from the Earth, because I told you that if you stay nearby the Earth, that's gravitationally too noisy. So we went to the Lagrange point 1 of the Sun Earth system. It took us a month. We could practice turning on the instrument, which is always a good, nice surprise when the instrument gets back to life. And on February, after a couple of months navigation, we released the test mass. I told you that we blocked the test mass at launch, and we had to release in flight. This is a mission critical operation. If it fails, you have no mission, because the test mass, instead of free flying, is blocked. And you see here the traces of the test mass position going into the center and being controlled by the electrostatics. And this is my project manager, which a person that never smiles, but he was so happy that we had passed this critical thing in 2016 that he was dancing by happiness. So let me try to march fast toward the conclusion, what we were asked to achieve and what we did achieve. So we were asked, these are the LISA requirements. So we had to demonstrate that we could achieve test mass accelerations below this yellow line, below the gray line. But ESA said, well, we don't want you to spend a fortune. So a standard practice in engineering is if you can demonstrate something within a factor 10, then you can extrapolate with good engineering. So please demonstrate that you can do a factor 10 worse than LISA, and the rest we will extrapolate. So instead of being below this yellow line, just stay below this blue line and we will be happy. Even more important, instead of going to this very low frequency, I told you this is a day. So if you want to do a meaning test full of some equipment at frequency of a day, you need weeks and weeks, and this is very expensive. And so ESA said, if you demonstrate things from a millihertz up, we will be happy. 20 minutes up, right? That's what a millihertz is. And what we were expecting to achieve, well, the performance budget of LISA is a book, is 280 pages, but there were 2 or 3 top entries in this error budget, and they are described here. At low frequency, we were expecting that this need of us to apply a little electrical force to the second test mass, which does not belong in LISA, so it's a limit of the test, would have been noisy, because we generate force with electrical field. Electrical field, you use a voltage generator. Voltage generator are noisy, and so you make a force noise. And it turns, if you calculate the things, that the more force you want to apply, the more noisy, the more noise for a given quality of your voltage generator, the more force noise you're doing. Actually, the way we do is the setting that counts. If you're set the system to apply 1 Newton, you make so much noise. If you want to apply 2 Newton, then the noise doubles. This plateau here, this bottom thing, the sweet spot here, we were expecting to be limited by the Brownian noise, the thermodynamics noise due to the collision of the gas molecules with the test mass. Brownian noise is a fate of all the gravitational wave detector. In our case, we do vacuum, but there is a residual pressure, 10 to minus 5 Pascal, and the collision of the molecules with the test mass gives enough acceleration to limit the performance of the detector. And then at high frequency, we were expecting to be limited by the interferometer that measured the acceleration. We didn't need a picometer per root hertz interferometer, but because we were flying a LISA demonstrator, we flew 10 picometer per root hertz interferometer. Here, the interferometer, the motion of the test mass is so small that you're only seeing the measurement noise. And we went to operation on March 1st, and these are the results, the black points, and we were bang on the prediction, which was much better than requirement. So we immediately opened champagne bottles, and it's very reassuring that you're close to what you have predicted. And everything was close to the prediction except the interferometer that you may notice is 10 times better than expected. Actually, more than 10 times. So we were expecting to do 10 picometer, which was we could demonstrate on ground, but the interferometer worked at 35 femtometer, and recently we have published the paper analyzing the performance. And basically at high frequency where we can see the interferometer response, the interferometer fits the noise model, the intrinsic sources of noise model for such an interferometer. But I have no time to go into this. And so we were limited at low frequency where mostly matter by the electrostatic force noise that we had to apply because we have to compensate. The main reason to apply this electrical force was to compensate the fact that this big chunk of material here attract this test mass gravitationally. Now, if you try to compensate this big pool all with an electrical field, you're bound to fail. That's too noisy. So we took a two-staged approach. We calculated the gravitational field, marking down the mass and the position of everything, including screws, right? And so we numerically calculate the gravitational field and machined a very dense test mass, compensation mass that we put very close to the test mass. That's a dangerous game, right? Because if you're wrong, you're making the problem worse. And so the name of the game is, what is the accuracy you have in calculating this field? And putting all the margin we could put, well, we thought we were able to compensate to 0 plus or minus basically a nanometer per second square, a fraction of a nano G. But it turns that the industry and the colleague had done a much better job, and we had compensated to 25 instead of 60 or 650. And so when we noticed that, we said, okay, let's crank down the authority and go to 25. We went to 50. And as soon as we did that, I don't know if you noticed the cartoon, we went from the black points to the red point. And so we went better than the LISA requirement. You may notice that even the Brownian noise plateau went down. And the reason for that is that we kept pumping, we vent the test mass to the outer space, and that works like a pump. So this plateau here kept going down with the vacuum around the test mass, a very expensive vacuum gauge, the Brownian noise. And so by the end of the mission in February 2017, we had gone so much down that now not only we have achieved our requirement, but we had surpassed the LISA requirement by margin all over the place. And so this was a little moment of triumph for many hundred people that had worked hard to this experiment. LISA Pathfinder was not only that. Here you see the list of papers we are producing. We're not finished yet. I can give you an example. For instance, where people had calculated over the year how much the test mass would have been charged by the cosmic ray. These are cosmic rays, they hit the spacecraft and produce secondary showers. So with these tools in high energy, J4 and other thing, you can calculate how much charge you get. And the main problem you have is that the charge which is deposited on the test mass is a random process. And so if you have any electrical field across the test mass, any potential drop across the test mass, you have a force which is a random charge times a static field. And so you have a random force. And so we could measure if the statistic of the charging is the one we were expecting. So we measured the spectrum of the charge. We found in very good agreement with Poisson statistics. We could also detect the noise, the force noise due to the random arrival of charging, and even more important, we could demonstrate that by applying a compensating voltage, we could kill this source of noise to the LISA requirement. There are other experiments, but I think my time is over. We detected the impact of micrometeoroid with the satellite, so we published paper on micrometeoroid statistics. But the most important thing is that now LISA is marching toward its implementation. We are now in an extension of phase A, will be followed by phase B, by phase B1, and we have a critical milestone that in the ESA jargon is called the mission adoption. Here the big money start to flow and you build the real flight hardware. So this is our next big milestone, and this should happen in 2024. Unfortunately, the phase A study in the LISA system, in the ESA system, is made by two competing industrial contractors. So everything is covered by industrial secrets. So I cannot show you the progress on the design. I'm very sorry about that. It's embarrassing. So I can show you, however, how we entered in the phase A. And this is how, according to ESA, this is the basic concept on which the two contractors are working to make a real detailed design of the mission. In the meanwhile, there are a few key technology development that are taking place. I have a few examples. For instance, the optical bench that was assembled by hand at University of Glasgow with this silica bonding. Now LISA has 6 optical bench, much more complex. So no way you can do this by hand. So UK and the UK Space Agency is setting up the technology to do a robotized assembling of the optical bench. There are a few subtleties in the interferometry, how you connect two measurement to nearby harm of LISA. This is an old problem, how you connect with fibers, and this is also going very well. And for instance, NASA, among the NASA responsibility in the mission is the telescope to exchange the light, a very critical item, and also the telescope is progressing very well. A lot of people are working to LISA in a very different role. We have a LISA consortium that includes the people that are working to the experiment and the people that are working to the gravitational wave science. It's now 1,400 members. So if you want to join, please, you're very welcome. And you see here the link. And so I think this 1,400 people are very hard working to open up the space-borne gravitational wave astronomy. And over the last year, we have been joining in this effort by equivalently enthusiastic group in China, but both the Taiji and the Changqing mission. And we hope that all together we will start this field as soon as possible. And so thank you for your attention, but also thank you to the fantastic team that allowed this incredible effort. Thank you.
Okay, thank you so much, Professor Vitale. Very comprehensive and complicated talk, I would say. You know, it's a lot of engineering. Yeah, it's amazing how could you manage to do that. And
thank you very much. Can you hear me?
Yeah, I can hear you. Can I stop sharing the screen?
Yes, absolutely.
I think I did. Okay, stop screen sharing. Okay, so that I can see you. Okay.
Okay, perfect. So we have already a couple of questions. Thank you very much for the outstanding presentation. We have right now more than 1,000 participants, 1,000 participants. So it was a success. The first question that we have here in the chat came from Hugh Hudson that says, the sun has P mode and convective noise at a few megahertz. Is there any way that these may become a source of noise for LISA?
No, actually, that's a very good question. G mode, P mode, I don't think we can, I'm not confused, but I know that there have been a paper in the past showing that LISA can detect the modes, some of the modes of the sun. This will be discriminated from the other signals. You know, it's not noise. They have a frequency fingerprint. The way the data will be analyzed in LISA is basically by making an enormous fit to all the sources, right? Bayesian estimation of all the sources. And those, if demonstrated that they are detectable, will be included in the fit. So it's not a noise, but a hope that we could even contribute to solar physics.
Thank you very much. The following question, next question is, can LISA detect the Big Bang?
Can LISA detect the Big Bang? So among the objective of LISA is that of detecting primordial stochastic gravitational wave background. In some scenario of the Big Bang, there is a mission of intense enough stochastic background that should be detectable by LISA, maybe even by the ground-based. However, those are scenarios, right? In the standard roll-off inflation, the stochastic background is too weak to be detected by LISA and by the ground-based detector. But there are those scenarios, including string scenarios and so on, that predict some rather intense stochastic background. Actually, in some of the scenarios, the stochastic background is so intense that that one could be noise for the other sources. But I don't think those are very realistic.
Thank you very much. Next question. Would seismic waves generated by planets be detectable by LISA?
Don't think so. The planet is too light. So I don't think so, no. And also, like those microhertz, I really don't think so. Because these are too light. The mass is too small. I never did the calculation, never read a paper, but by intuition, ballpark, we are off detectable things.
Thank you very much. Next question: should the interior of the cages of the test masses be charge-free? How did you manage to do it?
Say it again. I didn't understand the beginning of the question.
Yeah, should the interior of the cages of the test masses be charge-free?
Yes, but that's grounded. But there is a grounding to the rest of the spacecraft, and so charge is dispersed. If there is charge accumulated we paid a lot of attention not to have isolators exposed to the test mass, because those can accumulate substantial charge that cannot be discharged. However, that charge generates stray voltage, static stray voltage that would interact with a noisy charge. We have the ability to compensate that voltage with purposely applied voltage, which is quite enough that doesn't add to the noise budget. So, but we put a lot of care not having isolators exposed to the test mass, all conducting surfaces.
Thank you very much. Next question: what kind of gas was inside the test mass cage?
What kind of?
Gas.
Gas. It's mostly. I mean, the residual gas is mostly water. As usual in the system, is hydrogen. Is the classical composition of a vacuum system, because we do some bake-out on ground. I mean, that's an interesting story. You do the bake-out on ground, then you seal this thing. And then, Hindus has to assemble everything. And so it takes months before you launch. So the reality is that when you get to orbit, your vacuum system is full of outgassing. And then you open up this venting hose to the outside of the satellite and start pumping down. And we expect, a simulation on ground, we expect that most of it is hydrogen, as usual, that permeate all metals. Water, a little argon, unfortunately, which is a bit more noisy, and basically that's it. A standard composition, like if you were in a laboratory in your university doing the vacuum in a big tank, and not a especially fancy vacuum, right? Because at the end of the mission, we were 10 to the minus 6 Pascal. 10 to the minus 6 Pascal.
Thank you. Next question was submitted directly in Chinese. Ideally would be in English, but I've translated it. And the question is, how do you assess the disturbance factors to maintain high accuracy of tests?
How do you...
How do you consider these disturbance factors that might interfere with the accuracy of your tests?
Accuracy, you mean systematic error? No, we have some way of testing the noise in flight. And certainly LISA Pathfinder, that's what we did. We tested the noise. So in a sense, having flown LISA Pathfinder, we have an estimate of how much is the noise. And this estimate will be extremely useful in LISA. There are configurations, combination of the signal of LISA that are not sensitive to gravitational waves, but are sensitive to noise, and that will be the way we calibrate the noise. And the noise is the noise, right? The big signal will be well visible above the noise, and as you go to lower signal with lower signal to noise ratio, you will start fighting against the noise. Accuracy is not a big problem. We have a group studying calibration of LISA, but in reality, it should be okay. What happened? I only see me.
Yes, for some reason I can't turn on my camera. I see Professor Ip has disappeared. We have another question from Leonid Gurvitz about history. To which extent...
About?
History.
History. Yes?
History. Yes.
He's
To which
Storia.
extent, esatto, storia. To which extent does LISA follow any experimental development of the Sorel concept of the early 70s, from which, in a way, ESA science program has begun?
Okay, in the early, that would require another talk. So in the early 70s, the first proposal was a rigid structure. Ray Weiss was involved in that. The proposal of a LISA as we know it is a proposal from Pete Bender and can't remember the other name, a Nobel Prize. Well, sorry, I'm an old guy, which came up in the late 80s, mid 80s, right? And basically, that's the concept, right? It was very robust. Initially, it was 6 satellites because we didn't know how to host 2 test masses on a single spacecraft. But already in the late 90s, we had gone to 3 spacecraft. And from there on, it's a very solid concept. So yeah, by all means, is an heritage of the proposal by Hilse Bender, right? Yeah. And Peter is even older than me, but is still active in the team, by the way, Pete Bender.
Thank you. Can you tell us something about the Chinese plans of space gravitational waves missions?
You should ask them, right? You should ask them. And my information, honestly, stopped at the pre-COVID situation because the traveling stopped. But you know that there are 2 groups. One of CAS, of the Chinese Academy of Science, and one in southeastern China at the Sun Yat-sen University and Wuhan. Taiji, my pronunciation is horrible, but Taiji and Changqing. They are a slightly different concept, with Taiji being very close to LISA. And what we know is that I think both groups has flown some sort of demonstrator, not as ambitious as LISA Pathfinder, but a beginning of putting hardware in space, and so to self-train the groups to access to space. I know that they are very enthusiastic and very determined, and an old dream of us is that if at the end we have one Chinese detector and one Western detector, they could operate together, because there is an enormous added value if you have 2 similar detectors acting together in 2 distant constellation. You could put one ahead of the Earth and one trailing the Earth, and the triangulation you do with these 2 detectors would be amazing. And so we hope that we can both succeed and have a substantial overlap of operation. But we'll see. As I said, the detail of the development now, I'm not really up to date, mostly because of the COVID blackout.
Okay, thank you.
Sure.
One last question as time is up. From Amarin Pimno. He asks, why do we have to know about gravitational waves and how to use them? It's maybe a question that we could have been handy at the beginning of the seminar, but
yeah, but it's a very quick answer. It's the most impressive astronomical investigation tool, right? So think that 95% of the universe does not emit any electromagnetic wave, while everything generates gravity, right? And so a gravitational wave have been detected first time at the end of 2015. And now it's already a mature field, gravitational wave astronomy. Papers and papers and papers about the structure of the galaxies and the universe and the black holes. So it's astronomy, it's a new astronomy. So if your question is why we need astronomy, then there is a very nice quote from Plato in a discussion why you need astronomy. You can find on the CERN website, but there is no time to go into that. So I like astronomy, so I think it's a useful thing, astronomy.
Thank you very much.
Sure.
Perfect. I think, again, time is up. And I also see we don't have any further question. I would like to thank you once again very much.
My pleasure. Thank you.
For this excellent presentation that, as I said, we had 1,000 people, 1,000 people and more connected. So it was very successful and very interactive. And maybe if Professor Ip wants to say a couple of words, I will give the floor to him. You're muted, Professor Ip.
You're muted. You're muted.
Yeah, we can't hear you.
Okay, now you can hear me. So I said that I disappeared in the middle of it because Professor Vitale was doing so well and so convincing. Just let him sing and dancing. Right. So it's great, to hear this very fantastic mission. And as he said, he's going to come back to speak about the history of the gravitational waves. Oh, but I have a question, because you mentioned that the seismic waves is too weak to be detected, and we know that during the formation of planets, we have like the moon, the impact of the moon, formation of the moon is due to impact between planets, a mass-sized object colliding with Earth, and hence producing the moon and Earth system. Would those be detectable? We believe that those things must be happening all the time.
I don't think so, because, well, I don't know. I don't know. The answer is I don't know. I know that we can detect the effect of a planet orbiting a source, right? So you detect the wave from the source, a binary, and the planet passing by deformate the orbit such that you detect the effect. Right now, a collision of two planets, is that a fast process? Then you could be too high frequency. But a binary planet, I'm positive you cannot detect. The gravitational field is too weak to be detected, unless it's happening, in our solar system, obviously. But that's not the case, right?
Okay, very good.
Okay.
So, Laura, do you have any announcement afterwards?
Yes, we do. We have our next Something to Come webinar. It's going to be on the 6th of May, actually 5th of May or 6th of May, because it depends on your time zone. It will be here in China. It would be at 10 a.m. because our speaker is Cheng from NASA, and he will talk about the DART mission. And since he's based in the US, for him it will be the evening, and for us it will be the morning. This is maybe not very convenient for the ones in Europe, but as usual, we will publish the video, the recording of the webinar, and as well as, of course, the recording of the webinar of today with Professor Vitale. So if you follow us on Bilibili or on YouTube or our social media accounts, we have plenty, Twitter, Facebook, WeChat, and so on, you will also able to see the recording of this webinar. To keep it brief, thank you once again, Professor Vitale. I'm sorry for not being able to turn on.
My pleasure.
Thank you. Yes.
Arrivederci.
Arrivederci. Thank you, everyone. Bye-bye.
Bye-bye. Thank you. Bye.